Myself Omkar Navin.
And my name is Jiman sir.
Shivani Roy.
So we from S4 batch, we are going to present the problem statement for Maths ISC. So our problem statement is basically a problem which is related to a real life statement in which there is a water dispenser. There is a water dispenser and we need to calculate the amount of time required to fill a water of glass when the dispenser is 25% consists of 25% of water. So first we will compare and solve it. So basically when the time required for filling the glass when the water is 100% filled, and the second problem, the main problem is when 25% water is there, what will be the flow rate and the time to calculate the time required to fill the glass. So basically
This is what is said as a setup. There is a capillary and the water is draining from the bottom. And in the equation that is given was that is the derivative of y is equal to the minus k and y which is the water level.
what is meant by y?
So y is the water level. In the level.
Yes, and this is the equation that was given to us in the question, and we have to integrate it and basically find out the water time required to fill the water.
S is equal to minus ky is given to you.
Yes, in the equation.
Yes, okay.
And behind the flow, introducing Torricelli's law. So basically, this problem has Torricelli's law behind it, which is related to Bernoulli's principle. This basically gives you an idea about how the water flows and what is the rate of water flow when water is fully filled in the container and when it is partially filled.
Now this is our setup. We take an example of school cafeteria. There is a dispenser of 20 liters capacity. The dispenser is filled fully. Then it take fill the glass 2.1 second. And our goal is to calculate when the water level goes level lower. Then what is time for filling the glass? And there is we using differential equation and fluid dynamics principles.
So here we use the Torricelli law to determine the flow of water. That when the container's water level goes down, then what will be the velocity? So then when the water level goes down, the velocity of the water decreases as we before the water. So and this law is also derived from the Bernoulli's equations.
So basically now we consider the scenario as we know the problem statement that 25% of the water is left and we need to calculate the amount of water, the amount of time that needs to be filling the glass, because when the water was 100% filled, it took 2.1 seconds. So now you need to calculate what will be the time required to fill the glass when the water level is 25%. So this basically y is the water level basically, and this is the equation that was given to us in the question itself. So basically we will relate this into the equation and solve the problem.
This is our problem. To solve the problem, we need to determine the time it takes to fill glass when dispenser has 25% of its water left. Given the differential equation, y dash is equal to minus k root y. To solve differential equation, the differential equation is separable differential equation. Dy by dt is equal to minus k root y. Separating variables, dy by root y is equal to minus k dt, and then we integrating both sides. Integration of y raised to 1 divided by 2 dy is equal to integration of minus k dt. Then it gives 2 root y is equal to k minus kb plus c, determining the constant. When the dispenser is full, let's assume the initial water level is y naught 80. Let's put 80 is equal to 0, t is equal to 0 and y is equal to y naught. then equation will become 2 under root 2. And its gives c is equal to 2 root y naught. So the equation become 2 root y is equal to minus kt plus 2 root y naught.
So we are given that when the container is full, it takes 2.1 second to fill a glass. So when the volume of the container firstly the water is filled at the top level. So when the volume decreases, that achievement will be here. So let it be the delta y change in the volume. So to get this, to get the time to calculate the flow of the water at this level, we use this equation. And also, when the volume is constant and the time taken to fill a glass is inversely proportional to the rate of flow. So then also introducing the constant rate to make this proportionality sign is equal. So when the differential is full, the y0 to y0, we are given the time that I also said.
So basically in this equation, as you mentioned, so basically for 25%, here we talked about 100% and here we are talking about 25% of water. So basically y is equals to 0.25 y naught. So dx be the time to fill the glass. So for 25% of water, how much time will be required in order to fill the glass? So dx is equal to a upon a under root 0.25 y naught, because 25 that is this was 100% and this was 25%. And as we calculated a upon k into 0.5 as root goes and 0.5 is the value under root y naught. So we separated a upon k under root y naught as the value is given here 2.1 for 100%, and for 25% we substitute the value in here. So 2 into 2.1 and this is the value we get 4.2 seconds. So therefore for 100% it was 2.1 second, and for 25% of water to fill a glass it will require 2.4 seconds to fill a 4.2 seconds to fill a glass.
4.2 glass.
Sir, we substituted the values, we actually calculated for 100% and then we did it for 25%. So while substituting the value, we already have this value we calculated here, so we substituted it in here.
2.1 into 2 is a 4.2.
Yes. The key takeaway and practical application of our problem basically.
So the model y dash is equal to minus ky demonstrate how the rate of change is proportional to the quantity itself.
So basically this is not only limited to educational background, but this can be applied to various scenarios in real world problems like radioactive decay, population growth. This method can be applied in order to calculate real world problems like
Real world predictive power. Understanding the relation allows to the predict fluid behavior from a school dispenser to industrial tanks just by knowing the initial parameters.
So design implication is used here. As an engineer, we apply our knowledge about fluid dynamics and mathematics in order to solve a real world problem, and this was a small example of how we implement those two laws. As we saw here, the Taurus-Series law, which was derived from the Bernoulli's equation, was also used, and the mathematics which was used to convey the problem for giving a solution. So basically fusion of both fluid mechanics as well as mathematics was delivered here in design implication.